Good morning, everybody, and welcome to this session on precipitation in Africa, the future of observation, nowcasting and forecasting. I'm Caroline Wegman, and I will be the facilitator of this session. First, some technical things. Please switch off your camera and your microphone when you're not talking. When you have a question, please use the chat. Our technical assistant, Eva, will be looking over that chat and will come back to us when there are urgent questions to ask. So next slide, please, Eva. Oh, and I have to say this session will be recorded, so please be aware of that. So first, very shortly about me. I'm Caroline Wegman. I work at HKV. I will give a short introduction of the HKV as the facilitator of this session in a minute. I'm not an expert on precipitation data, but I'm actually using it quite a lot. So that's why I like this, this session in the way that for example, all kinds of disaster risk reduction and of course understanding risk, that's what this session is for. You actually need, of course, this precipitation data. I am myself more involved in rivers and coastal systems and in nature-based solutions. But as said, I use a lot of the mostly satellite precipitation data in my daily work. So I'm very excited to be part of this session, and I hope I can learn a lot as well from our speakers. But I will be focusing on the practicalities of using these kind of innovative satellite solutions, or satellite and other kinds of measurement solutions, I have to say. Next slide, please, Eva. So then shortly about HKV. I work at HKV, and HKV is a water and safety organization which has a lot of knowledge entrepreneurs in it, working since 1995. We are based in the Netherlands, and we have around 73 employees, which is very knowledge driven, as we call it. So over 25% of our colleagues has a PhD or is a PhD candidate. So we invest quite a lot of money into our research and development within the company and outside the company. About 10% of our budget is spent on this. And we work on in many fields and many teams, but just to summarize a few, it's of course flood risk, water resource management, rivers, coasts and deltas, climate change, crisis management, evacuation and stuff, data science, data management and operational water management, and so on. So everything that is related to water, and then mostly in the extremes, droughts and floods, we work on in the Netherlands, but also abroad. So I just wanted to give you a quick introduction on that because HKV is hosting this session. Next slide, please. But of course, this session, oh, that's the previous one. This session is not about HKV or about me. It's about precipitation in Africa. And so as I mentioned already, of course, we will have in a bit, we will have 4 pitches of innovations in this field in how to measure or look at precipitation data. Because how this fits in understanding risk is that, of course, for flood risk management, you actually need quite reliable precipitation data for measurements and forecasts. And why are we focusing on Africa specifically? A lot of the innovations can also probably be used in other parts of the world, but in Africa, that's the largest data sparsity. And what we mean by that is that actually there's quite little measurement data available for Africa. This image on the right does not give all the measurement facilities in Africa, but it gives quite a clear example of the distribution and the lack of data measurements in Africa, and especially that, of course, parts of Africa are not covered at all by measurements, which our speakers will talk about later, how they try to solve these bars. I see we lost the screen now, Eva. Let's wait for that for a little bit. She's starting it again. So let's go to the next slide, please. So who will you have talking today? So as said, we will have 4 experts talking on their innovative solutions for precipitation, measurements, and usage. This is great. And afterwards, we will have a panel discussion. So how this will go from now is that every presenter gets 5 to 7 minutes to pitch his solution. If you have any questions about this for clarification, you can ask them in the chat and we'll answer them. But please, for all the questions that will require some discussion, please save them, because at the end of all the 4 sessions, we will have a general panel discussion in which we will all can talk about the subject and the things that we work with. So only, then again, only for clarification questions, please come immediately within the presentation or immediately after with your question. And for all the other questions, we use the panel discussion afterwards, for which we will have enough time. So first of all, I would like to present Mr. Frank Annor, who works at the Trans-African Hydro-Meteorological Observatory. And his goal, or the Trans-African, or the TAHMO goal, is to install 20,000 low-cost stations across Africa. And as of course seen in the image before of Africa, this is quite needed, Frank. So I would like to say, Frank, the floor is yours, and very excited to hear about your ideas about this.
Thanks, Caroline, and thanks to all participants and co-presenters. So this morning I want to discuss some of the new sensing methods that we have as TAHMO, but more in the framework of the Trigger project, which is a Horizon 2020 project. It is led by the Delft University of Technology, where I am as well, and then TAHMO is a partner on the project. Next slide, please. So we have, on the project, we have about 18 partners. 10 of them are from Europe and 8 of them are from Africa. And of course, the nice thing is that we look at businesses or SMEs, as well as universities, both in Europe and Africa, working together to bring about some innovations to help us understand our water, weather, and climate much better. The next slide. So at the moment, we work as TAHMO, we work in 23 countries in sub-Saharan Africa. But for the project, we are concentrating on in 5 countries. That is Uganda, Mozambique, South Africa, Ghana, Kenya. So these were the countries where we were concentrating. And more, it's about agriculture, flood or disaster management, insurance, as well as renewable energy services. Yeah, next slide. Now, the thing is that when you look at understanding rainfall, we have to combine a number of data sources. So, of course, satellite base is very important, but also in situ data sets are very key, especially in understanding our rainfall patterns and improving our weather forecast. But just having the satellite data and the in situ data is not enough. You need to also assimilate the data. So your model is also as equally important as the data sets that feeds this model. But after you have developed this and you have, let's say, forecast or products, you need also the end users to be able to help you improve the product that you have or validate the product that we have. So all these are very key elements, especially in understanding rainfall or weather in Africa and the rest of the world. The next slide, please. So here I would maybe talk more about the in-situ sensors. Here, mainly it is important that, of course, the satellite gives us a very good overview. So you have a larger spatial extent, but often you might not have the details that you might want because of the spatial resolution. The other thing is that sometimes you also need a wider coverage, but your in-situ sensor alone cannot provide you that wide coverage that you need. Roughly we say that one station covers a distance of about 30 kilometers, or if you want an area, about 900 square kilometers. So if you're going to use only the in-situ sensors, that might not help. If you only want to use satellite data, that might not help. So basically, the idea is that you need to integrate all these data sets, and that is where you get some value for the understanding of rainfall products. Yeah, next slide. So coming back to the in-situ component, TAHMO decided to increase the density of the network, as Caroline showed on the slide, that we realized there's a very big gap in Africa. And to bridge the gap, it meant that we don't need to replace existing stations. We need to make sure that existing stations are still functioning, but at least we need to then add extra stations to improve the density. And to do this, we needed stations that were cost-effective, robust, needed very little maintenance. And that's why you see this, the station on the extreme left-hand side of the screen, which is a TAHMO Generation 3 station. But in certain places also, these stations are normally installed at 2 meters, but in certain locations or sites, you might need to also have this at 10 meters. So we are also able to add extra sensors to the TAHMO standard stations to be able to have stations measuring wind speed, let's say at 10 meters, and also measuring precipitation and other weather parameters, standard of about 12 parameters being measured. But even that, when you look at the cost of the station, which is sometimes about 10 times less in terms of the cost to traditional stations, it's still a bit expensive, to be able to have the variability of rainfall that we really need to monitor. So we also designed a disdrometer, which is on the extreme right corner of your screen. At the upper part, we have what we call an evaporometer, and below we have the disdrometer, which measures rainfall. And here you realize that with the disdrometer, maintenance is almost, it's almost negligible. Of course, you need to dust it from time to time, but aside that, really no need for difficult maintenance. Can we go to the next slide where I will delve more into this? So the disdrometer was coined from the idea of intervalometer, a rainfall measurement that is measuring rainfall droplets. And this is really very nice because with this set of sensors, the idea of rain gauges clogging and stuff is actually reduced. So this also using household gadgets, which are very cheap. And these sensors, the idea is that we'll be able to create rainfall sensors less than $50. Of course, they also need to meet the WMO requirements. So often you are torn between cost and also meeting reliability and WMO requirements. So these are some of the sensors that we've developed so far. The next slide.
Frank, you have 1 more minute.
Yes. Maybe let me jump to the next slide then. So this is also the evaporometer, which helps us to understand evaporation. But of course, while we are measuring evaporation, also we are measuring rainfall. So we produce or we provide redundant sensors because rainfall is a very difficult parameter. And if you don't have redundant sensors to measure your rainfall, then you are really in trouble. So we introduce a lot of redundancy in our station network. The next slide. Of course, we also look at lightning because that also helps us to understand rainfall and also to validate the measurements that we are having from the sensors and as well as the satellites. So we also have lighting sensors on our stations. The next slide. We've developed what we call the GNSS, which is the Global Navigation Satellite System, which looks at the signals from the satellites and how they attenuate with the atmospheric moisture content. So this has been developed quite recently, and we are testing this in Tanzania and in Ghana. Basically, it's the same idea that probably Aart will also present, but now using microwave links. So this is also new innovations to be able to help us understand better the atmospheric moisture content, which determines our rainfall patterns. The next slide. We also encourage schools to be able to have simple manual rain gauges using just bottles, and then with an app also be able to record the measurements and send this automatically via an ODK app that we have developed. So we're also testing this in Ghana, also to help densify the network that we have in terms of rainfall monitoring. The next slide. Aside all this, of course, you don't just need to collect data, but the data has to be used. So we've also developed, for example, in Tanzania, together with the World Bank, where we have a portal for flood early warning system based on observations as well as models. So just an example. Thank you.
Okay, thank you very much, Frank. I think that's very interesting also to hear how you combine all the different sources of data. We will go straight on to the next presenter. So for any questions, please leave it to the panel discussion afterwards. We will now be listening to Mr. Aart Overeem, who works at the Royal Netherlands Meteorological Institute, also called the KNMI in Dutch. And he derives precipitation amounts using commercial microwave links from cellular telecommunication networks. I'm very interested about that. Please take it away, Aart.
Yes, thank you for the introduction. I would also like to mention my co-authors. So this is actually a joint collaboration between KNMI, but also Wageningen University in Research, the GSM Association, and currently also Delft University of Technology and derives. So my other co-authors are Tommy van Let, Hidde Leijnse, Jan Priebe, Daniel Trickerico, Ruben Imhoff, and Remco Uilenhoed. Next slide, please. So what is a CML, and how can you measure rainfall using a CML? So a CML is a commercial microwave link, and it actually consists of a transmitting antenna at one telephone tower or radio site, which sends signals to a receiving antenna at another telephone tower. And mobile network operators, they often store the received and transmitted signal level data from these microwave links to monitor the stability of the network. But in case of rainfall, the signal is attenuated. And well, the more rain droplets you have and the larger the rainfall intensity, larger the size of the droplets, the more attenuation you get. So by comparing the signal level data from a rainy period with those from a dry period, you can compute the attenuation due to rain. And by converting this attenuation, by using a formula, you can convert this attenuation to a path average rainfall intensity. So with CMLs, you are able to estimate the rainfall intensity between telephone towers. And the map shows locations of microwave links. Well, typically they vary from 100 meters in length up to 15 kilometers, sometimes even more. So in principle, you can estimate rainfall for all these lines plotted on this map. Next slide, please. Well, why do we need CMLs? Traditional rainfall observations are from radars, where the coverage is shown in the upper left panel. And as you can see, coverage is sparse over many areas, especially over Africa. On the left, the bottom panel, you can see the distribution of rain gauges from one particular data set, and also, again, sparse densities across Latin America, Africa, and also Asia. And on the bottom panel on the right, you see an example of a satellite product. These are, of course, very useful, these precipitation products, because they provide coverage over areas where you do not have any other rainfall information. But generally, they are less accurate than ground-based rainfall observations. And well, then the upper panel on the right shows you a mobile coverage map. That means you can use your mobile phone in these areas plotted in green and in purple. And that means that usually you will also have CMLs somewhere around. So in principle, you could get rainfall estimates from these CMLs for those areas, and that could vastly improve the coverage of rainfall measurements. Although the CMLs have not been designed to measure rainfall. And the nice thing is that the infrastructure is already there. So there are roughly 5 million CMLs worldwide. So in principle, you could derive rainfall for an enormous amount of locations. Next slide, please. So this shows you, perhaps you could click on the image. Yes, thanks, Eva. So this shows you an example of rainfall maps solely based on CML data. This is for the Netherlands. On the left, only based on CML data. On the right, it's based on radar and gauge data, a climatological data set. And you can see that the mobile phone network is able to capture the rainfall dynamics, to capture local rainfall showers. So that works quite well, especially in summer. But the big question is, does it also work at a large scale for low and middle income regions in tropical and subtropical climates? And only a few studies have investigated this. And now we are currently, together with all these partners, upscaling this technique to show that you can really do this in those areas. Next slide, please. So this shows you an example from last year's pilot study done by Tommy van Lets. It shows you the locations of microwave links from one operator in Nigeria, so all those purple lines. And on the right, you see a map, zoomed in map for Lagos, the Lagos area. So there are thousands of these CMLs in this area. And so potentially they could provide data every 50 minutes. It could even be at higher temporal resolution. So then you have an enormous amount of measurements, especially if you compare it to the number of rain gauges in Nigeria. Next slide, please.
You have 1 more minute, Aart.
Okay, thanks. So what we see here is the top panel shows you a satellite, one of the most important satellite rainfall products, GPM iMerge. And on the bottom panel, you see the CML-based rainfall map. And as you can see, both capture rainfall, but the CML rainfall maps provide much more detail. And it also looks realistic. It seems that they can really follow the rainfall showers. Well, a big challenge is finding appropriate reference data. We're currently upscaling this technique in Sri Lanka, where we have 3.5 months of data. We are writing a manuscript about this, where we have quite some rain gauge data to compare with, and also satellite data. And for this, we applied our freely available RainRink algorithm. And also all the research groups who work on this topic also have their own algorithms. Next slide, please. So, yes, CMLs can also be used for tropical rainfall monitoring, but we need to upscale this technique to prove that the technique works. It's meant as a complementary source of rainfall information. And my colleague Ayan Drost is currently upscaling this technique in Nigeria. We now have 6 months of data, Sri Lanka and Papua New Guinea. And I also refer to a video on CML rainfall monitoring in Sri Lanka and a couple of use cases, what you could do with it. So thank you for your attention.
Thank you very much, Aart. I think that's a very exciting new innovation, and actually your presentation was well set up, because we got a question how it compared to satellite data, but then immediately you already answered it in your presentation. So that's great. Well, then we go to the next speaker, which is Mr. Bashiru Yahaya. Sorry for the pronunciation, from the Ghana Meteorological Agency. And of course, he has first-hand experience with the importance of rainfall information in Ghana, and he will tell us more about the efforts to improve precipitation observations and forecasts for Ghana. So please, Mr. Bashiru, take it away.
Okay, good morning, hosts. Good morning, my co-presenters and the panelists. My name is Bashiru Yahaya. I'm presenting on behalf of Ghana Meteorological Agency. I'm presenting on improving rainfall measurements and forecasts in Ghana, GMet nowcasting techniques for early warning system. To put it, nowcasting is a detailed description of the current weather information and forecast within 0 to 6 hours ahead of time. So this nowcasting employs the use of current observation through our network of stations. As the first speaker, Frank Annor, said, observations alone cannot be used, cannot be dependent on forecasting. You have to incorporate the use of satellite imagery and the numerical weather prediction product. As the second speaker, the first speaker said, is equally the numerical weather prediction products are equally important as the observation. We have, he also mentioned that in Africa, we have a sparse network of stations. So we also rely on satellite products. Recently, we received 10 automatic weather stations financed by World Bank. Also, we use the TAHMO products. Next slide, please. Next slide, please. So to put it, early warning system in effect is the set of capacities and structures needed to generate and disseminate timely and meaningful warning information. Here, the point of emphasis is timely and meaningful. That enables individuals at risk, communities at risk, and organizations at risk to prepare and act appropriately in sufficient time to reduce the harm of high impact weather. So you can see on my slide the effect of high impact weather. If these people have received some early warning signals, they wouldn't have been out there in the flood to be taken by surprise. So this affects the agriculture sector. It brings about food insecurity. It affects the energy disruption. It brings down the lighting system, also affects the electricity mast, and it also pollutes the subsurface water and drinking water, as a result of which brings about outbreak of disease. Next slide, please. And research has also shown that in changing climates, there will be frequency of increasing extreme events, and currently we have begin to experience such frequency. The Ghana Meteorological Agency did some research to find the impact, or to find the meteorological analysis of the flood events over Ghana, whether it is anthropogenic activities or it is solely by meteorological purpose, meteorological effect. But we realize that mostly is anthropogenic activities. Please, next slide. So, next slide. So GMet now casting techniques. Also, we also call it a poor man's ensemble. Use the observation. We look at the weather parameters like the pressure, R rate, wind. We look at global models like ECMWF and NOAA, Meteo France, and UK Met Office. We also look at the regional models like weather research and forecasting model. We also have this GMet sub-seasonal package for forecasting. Besides that, we also look at the observation. There is also a package called the nowcasting satellite application for forecasting, which is a project rapidly developing thunderstorm. Please, next slide. Next slide, please. Hello, next slide.
Yeah, I think it's already. Oh.
So hello.
Yes,
so
do you?
I'm sorry, there seems to be a delay between the...
And DMWF. Hello, next slide. Next slide, please.
What slide do you want?
Okay. Yeah, this one is okay.
Okay.
This is also from the Meteo degree 0, the application for forecasting, the rapidly developed system, and we use the satellite map station, and we get GMet. So you generating the forecast alone does not end there. You have to have a structure for dissemination system. And currently we are also working on the dissemination techniques and multi-platform dissemination system to get to the end users. Please.
Yeah, there's a bit of a
Next
delay
slide,
in the slides, Bashiru, but I hope this works for you now.
Okay, that's fine. So this is also the sub-seasonal, 1 week ahead of time. The first mentioned global ensemble forecast system, this 1 week ahead of time to generate the frequency or exceedance or probability of rainfall over the region. Next slide, please. Next slide, please. Hello, next slide. Okay, this is also the 5-day forecast on the 15th September 2020. These are the products we use for the nowcasting techniques. Next slide, please. So I think we are done with the presentation. I showed all the images. Thank you very much, and thank you for your attention.
Thank you, Bashiru. I think it was a very nice presentation. Sometimes we lost you a little bit with the connection, but I think it was, we were all able to follow. It was very interesting. Also, I'm glad you elaborated on the need for these precipitation data and what you use it for and why it is necessary to actually have reliable precipitation data, because we are, of course, at understanding risk here. So thank you very much. I would want to go to the next presenter. I'm looking at the time, which is Doreen Lucht, who works at HKV, and she applies machine learning to generate nowcasts from satellite observations. And she will tell us more about this. The floor is yours, Doreen.
Yes, thank you. Indeed, my name is Doreen Lucht. I work at HKV, and Caroline introduced, I will talk about machine learning for precipitation nowcasting based on satellite data. The model I developed together with my colleague Martijn van Hoek. And we first applied this for Ghana, but the method is easily extendable for any country in Africa. Next slide, please. The nowcasting we developed this year is actually part of a product that we developed in 2014, which was until now showing observations. It was developed together with our colleagues at KNMI, and it's showing rainfall observations for 13 countries in Africa. We have a website, rainsat.net, and an app for each of those countries. And now we are implementing nowcasting model for Ghana, Senegal, and Burkina Faso within Horizon 2020 program Leap Agri. And also the web page is being renewed, and from the start of 2021, it will show all countries in Africa. Next slide, please. So when I say that we are showing rainfall observations, what are we actually showing? We're showing observations from satellite, the Meteosat 2nd generation satellite, which is a geostationary satellite covering both Africa and Europe. And it has a temporal resolution of every 15 minutes, and on the sub-Saharan region of Africa, approximately 3 by 3 kilometers. And that makes this a product also special when we compare it, next slide. Yes, when we compare it to, for example, GPM, because the resolution is much coarser. Also the latency, so the time it takes for us to receive the data is much smaller. And well, in the applications that we are talking here, that is really important, because when we're talking about flash floods, those events, they generally occur very fast. I have to say that the GPM gives a better and more accurate precipitation intensity. But for some applications, it's more important to know that it will rain well in advance than the exact amount it will rain. So for those applications, we developed RainSat. Next, please. And we use the Severi component of Meteosat second generation, and we use the infrared channels, infrared measurements. And the advantage of that is that it works both at the daytime and at nighttime. The infrared measurements are converted to precipitation amounts by an algorithm called NIPE, Nighttime Infrared Precipitation Estimation, that is developed by the KNMI. It was at first calibrated on Dutch radar, and now since December 2019, it's also calibrated on GPM measurements. And these are the observations that we show in our website and our apps. And it's also the data that we based our machine learning model on. Can you go to the next, please? Yeah. Because the machine learning model that we are using is a neural network that was originally developed by Xi, working at the Hong Kong Observatory. And it's called a trajectory GRU for those who are familiar with machine learning. It takes a few hours of past precipitation to predict a few hours ahead. And Bashiru said nowcasting is up to 6 hours indeed. For now, we are working with 3 hours ahead, and if this works well, we want to extend it to 6 hours as well. The nice features of the nice features of this algorithm that she applied to radar in Hong Kong is that it trains the movement of the precipitation at different scales in different layers of the network, and it is able to catch decreasing and increasing intensities. And that is very important when you want to predict convective rainfall, which is the typical tropical, very short, very intense and small scale events. And those events, as they happen very sudden and they come with heavy rains, they are often a cause of flash floods. And more important, it is quite hard to forecast them. Also, Aart already referred to them. And that is why we developed this model, hoping to catch those events especially. Next slide.
Doreen, you have 1 more minute.
Okay. What you see here is some of the first results. We so far trained the model on half a year of data between December 2019 and June 2020. At the moment, we are also training again for the entire year, and we're hoping to train on more data in the near future. We are very happy with these results already, because you see that on the left is the observation of our Meteosat satellite, on the right is the forecast for that same time. And you see that it captures the movement of the rain quite well. Next, there's another event. Yeah, oh no, back, yes. We also see that it's capturing increasing and decreasing intensities. The thing that we hope to improve is the intensities, because they are still a bit off, as you can see here. But from our performance measures of the validation and the training data set, we can see that we are still expecting improvement if we include more training data. And that also brings me to the last slide of the next steps, because of course we would like to involve more training data. It is not part of this Horizon 2020 project that we are currently doing, but we definitely hope to do that in future. What is part of the Horizon 2020 is to implement this nowcasting model for 3 countries, Ghana, Burkina Faso, and Senegal. And well, we do have many ideas for development, both on the machine learning model or on calibration or any other efforts. So it is something that I hope we will continue working on over the next years. Next. That's it.
Okay, thank you very much, Doreen, for this clear presentation. So I saw some questions coming in for the chat, but first I want to thank all for presenters, for speakers, to show their innovations. And actually these presentations were given to give a first introduction of all the things that are happening concerning precipitation data. But I would really like to invite you now to post in the chat the questions or suggestions that you have concerning the innovations that we just heard, but also concerning possibly your own ideas about this or innovation about this. So we can go to the panel discussion from now on. So please, all the questions that you saved for the presenters, please ask them in the chat. I already saw two questions. One from Mr. Martin Venkel, as I say it, and he is asking you, Bashiru, if you could please send some URLs or titles of the publications that you mentioned, because they were very interesting, and especially on the frequency analysis of rainfall flood events. I see that already Maureen, who is a colleague of Bashiru, already sent some links in the chat. So I think that you already got your question answered then, Martin. Then we have one other question for Doreen. And that is the ML used to generate the rainfall retrieval or only to nowcast from existing rainfall products?
If to generate the rainfall retrieval, well, this we use to nowcast from the same data as we use for training the model. So we nowcast using the Meteosat satellite data, and that is also what we use as an input. But for future, we can see that you would also use data assimilation using, for example, the systems that Aart or Frank showed.
Yeah. Ben, can you jump in? Because I see you asked another question. Maybe it's more practical if you ask that yourself and can provide the right tone and what you exactly want to ask.
Sure. Yeah. Can you hear me? Right? Yeah. I see myself lighting up. Yeah. I just wanted. You talked about the values are a bit lower in the nowcasting product than reality. And this is something that I saw in so I'm quite new to machine learning and I'm just sort of getting into a similar field. So I saw it in the Google product as well that they developed, that the values were too low. And I wondered whether it's sort of just an inherent thing where the uncertainty in the possible forecasting outcomes essentially gets smoothed over, so the values get low. And I don't know how we address that, but I guess it's more of a discussion point than a direct question. But I'd be interested if you had any thoughts on how you go about fixing the values themselves being too low.
Yeah, it is definitely, especially because it also has to do with the performance measures that you define to train your network, and it's very hard to define performance measures that include all the aspects, and most of them will lead to an algorithm that prefers to predict a more smoothened image. But you're right, and you can do something with penalizing or performance measures based on thresholds that you really want to predict the high intensities well. But of course, that comes at a cost for the lower intensities. But in case you want to catch the convective rainfall, that might be a good way to go.
Yeah, I wonder whether if you were to sum up the sort of the total amount of water, I guess, if you did like the area and the amount, would it correctly get that right? And it's essentially just like smoothing it out over a wider area.
It might be the case, yeah. That's what we also thought.
Cool, thank you very much.
Thank you, Ben. I think that's a very interesting question for many people here who are dealing with machine learning and how to work with that. So we have another question from Nikki. He or she, I'm sorry, I don't know, is working in Mozambique. And Nikki, can you maybe share what you wanted to share yourself?
Okay, thank you. Yes, of course. Hello, everybody. Indeed, I'm Nikki, I'm a hydrologist, and I'm also from Holland, but I am since 2016 in Mozambique, and I work in water projects and agricultural projects. It depends. And I just want to share, I thought was interesting, we also work with 3 TAHMO stations within our current running Upscaling project. And actually our challenge is maybe not on the technical side, but it's more also on the sharing of the data. So like we currently share them in a format of a report, to all the interested people who are interested in rainfall data in Mozambique, because it's of course open source. On this, on who we can contact on how we should share our data. And I like the idea of you can get rainfall data from the telephone towers. So what would be the first step for us to get into that as well?
So I think that's a question to Frank, or more a discussion point. Frank, do you want to respond to that?
I think that's it's really nice to learn that your stations are installed and working. That is fine, and also for us to discuss how data is shared. I think this is a very fundamental problem that we really need to address. We've developed an online portal where people can easily download the data, especially if it's for research purposes. That is possible, and we also have an API. But for a layperson, this is already very difficult to be able to relate to. So of course, we are at the moment developing a more user-friendly portal in terms of visualization so that people can easily relate to the data that we have. But I think it's something that even all Met agencies, including GMet, are also looking at how to make the data really available to people without necessarily getting on the website or something. In other places, we have used IVRs, or what we call the USSDs, where people can request for information on rainfall amounts or forecast. But yeah, it is not easy. It's something that we still need to develop further. So I agree.
Okay, thank you very much, Frank, for that. I saw some other questions, but in the meantime, I would like to ask everyone joining this session to go to a website called menti.com. Use the code 638087 that you see at the top of my screen. And please tell us, what kind of data do you use as information source for precipitation? So we can get that discussion going as well. I will stop sharing my screen and go to the next question, and then we come back to this later. I will also post it in the chat, what is exactly the code of this Mentimeter. That would be really nice to know what everyone's busy with. So let's go to the next question in the chat. That is, what's needed for new countries to enter the RAINSAT or use CML, etc.? Most solutions seems to have been developed in research projects. Yet how much will be open source and what will be needed to start in a new area? What skills or investment costs are needed? So maybe Doreen, do you want to share something for that first?
Sure, and I think it's also a question to add, but yeah, I can start off. Well, indeed, RAINSAT is developed in research projects or other projects, and we are not a company providing operational systems so much. We develop within projects, and we like to continue this development, but at some point we like to hand, we don't want to be running this operational, and for now we are doing that. We hope to find another solution, and we do want this to be open and freely available. So it's not for us a commercial a way of commercial product. For us, it's mainly the development that we like. If you ask how other countries can join, well, in principle, it's very easy because the data is available for the entire African continent. So we only have to train the model on a different extent of the data. And that is in a very small effort, in fact. But for each country, it is a separate effort. Yeah, adding a different country would be really not a big effort.
Okay, thank you. Then maybe also the same question for Aart, indeed. Do you have anything to add to that?
Yeah, so, well, for CMLs, the problem is getting the data. So you need to negotiate with a mobile network operator, and several research groups have got data from several countries. So they are often willing to give the data, but it's also quite difficult to get the data for other regions. So with the involvement of the GSM Association, which represents the telecommunication industry, that can become much easier. But that's one obstacle. The retrieval algorithms to do the rainfall retrieval are actually open. There are a couple of rainfall retrieval algorithms which are available. But first, I think you need to look at the data from a specific country to do coupling of metadata with data, because that can widely differ between mobile network operators. Then do the rainfall retrieval. Then you can use existing code and validate everything for months of data at least. So it will require some additional research, and it really depends on where you are. For some regions, there already a lot of work has been done. And there is also a semi-operational product for Sweden. I just shared the link. So that shows that there is ongoing interest in this.
Okay, thank you very much, Aart. Marianne, was that the answer to your question?
Yes, thank you. I'll reach out to you guys.
Yeah, I just wanted to suggest that for more information. Of course, I think all the presenters are very willing to share more of their knowledge, but also to discuss with you how to work with these kind of things. One more question for you, Aart. What is the distance between mask for the CML, and what is the coverage for recording rainfall?
Yeah, so I think this refers to the resolution of the rainfall maps. This is something we usually set to a few kilometers, but it really depends on the actual link density, what the effective resolution of such a map is. So in urban areas, it's usually very high. It could even be higher than 1 or 2 square kilometers. But of course, in rural areas, there will be less CMLs. About 20% of the Earth's surface is covered, has mobile phone coverage. That means that usually somewhere in the vicinity, there are CMLs. So the coverage is quite wide, but obviously it won't cover the entire African continent. So of course, merging of data is very important. Satellite data with CML data, for instance, for Africa, where you only will have satellite data in the end for regions where you don't have CMLs.
Okay, thank you, Aart. Of course, it's already 5 to 12, so we have to wrap this up. I saw some more questions, so please ask them, the presenters yourself via email. You can find their details, of course, online as well. I just wanted to show you quickly what we got from the Mentimeter results. So it's nice to see that many people use different kind of data, but a lot use satellite or radar. And I'm of course quite interested what kind of satellite and radar, but sadly we don't have time to to go into that further. So I want to thank all you for this lively panel discussion, and also of course the presenters who were willing to share their innovations. Please reach out to us if you need more information or want to discuss things. And again, thank you very much for your attention and active contribution to this session. Thank you very much.